Okay, section 4.4 in the textbook starts with the definitions of concavity and the fact that certain functions can have a concave up and a concave down feel to it. This is really concavity is a science term, so some of you might be very familiar with the concept here. So uh, when we talk about concavity, we also talk about the point in between the two areas of concavity, this being a turning point, or commonly called a point of inflection. That's discussed. This is a discussion in 4.4, and we'll work through a couple of examples here after we talk about the definition of concavity. So by way of the picture here, there's a picture of a concave up or concavity upward function. It's pretty exaggerated. It might not be very obvious with some functions, but the general trend is that it opens upward. So the graph lies above all the tangent lines. Okay, the tangents rotate counterclockwise, and the slope of the tangent lines increases. So to the left, it'd be at -2, for example, and it goes through 0, and then it goes to a positive. Um, Notice that the derivative of the function increases, and the second derivative is greater than 0, and concave up intervals have a local minimum. Okay, and basically for concavity down, all of the reverse characteristics are true here. Graph lies below all of its tangent lines. It rotates clockwise. Tangents rotate clockwise. Slope of tangent lines decreases, and if the first derivative decreases, then the second derivative is less than 0. And concave up intervals have a local maximum, and those definitions are in your textbook explained here. And so when we talk about concavity, we often talk about a point of inflection. And a point of inflection is when the sign changes. Okay, so a point of inflection occurs at a particular point of the graph if the second derivative changes sign at this point. Okay, so it goes from concave up to concave down, and that goes through the point 0. When the second derivative flattens out, okay, it goes through 0, and on one side of that point, it's less than 0 or greater than 0, and then on the other side of that point, it's just the opposite. Okay, so for our first example of our graph here, right in this area, we have, okay, an inflection point at C, and it looks like it's concave down, or less than 0, the second derivative is less than 0, and then it turns to concave up, and it looks like the second derivative is greater than 0. Similarly, okay, we have a point here, and it's going from concave up to concave down through this point. Okay, and a point of inflection is found by taking the second derivative and setting it equal to 0. So here's some situations that we're used to and familiar with where we could have concave up and concave down situations. Okay, so there's a nice clear turning point, be like a cubic function, for example. Okay, here's a corner point, okay, and infinite slope points, getting concave down and going through turning points here. Okay, what else have we got? Maybe let's do an example here. Sure, let's find the intervals of concavity for this particular function. Okay, so I will pause, and you guys may want to go through this, and let's take the first derivative and the second derivative. I'm going to pause this temporarily and work through this, and we'll be back in a second. So take some time, please, and find the first derivative and second derivative. Okay, the first derivative and the second derivative are found. Now we're looking for the point of inflection. So we take the second derivative, and we set it equal to 0. That means we take this function, and we set it equal to 0 and solve for x. Okay, so let's take out a greatest common factor of 12x. That leaves me with x minus 1. Okay, so we have situations for x where we've got so we have 2 points, turning points here. Okay, we have 2 points of inflection. So I'm going to use a sign chart and do this. Okay, so as I go from left to right, my first interval is x is less than 0. I have an interval x is between 0 and 1, okay, and then x is greater than 0. And I want to take my second derivative. And my second derivative function I'm going to use, okay, is this one here. Okay, and I need need some points here. So let's choose -1, x is a half, and x is 2. And I want to use, okay, the function 12x multiplied by x minus 1. Okay, I'm just going to write that here so I have it. Okay, and in this interval when x is -1, I'm going to have a negative. Okay, let me just clean this up a little bit. Okay, so when x is -1, 12 times -1 is a negative, and -1 take away -1 is another negative. Okay, a negative times a negative is a positive. Okay, when x is a half, I'd have a positive and a negative. And a positive times a negative is a negative. Okay, and when x is 2, I'd have a positive. Okay, 12 times 2 is positive 24. And then 2 minus 1 is positive. Okay, so I have a positive interval. Okay, so what do we have here? This is concave up. Okay, this is concave down. Okay, and then it goes to concave up. I'm going to show this on the graph in Desmos, and I'm going to open that here first in a second. It's not so obvious to see the points of inflection here, and here's the function, the original function. So the first one is concave up at 0, okay, and then concave down to 1. So it's about the point right here. Okay, so the interval between 0 and 1, okay, is concave down. Okay, and hopefully you can see that sort of curve down. Okay, and then from beyond 1, so when x is greater than 1, I've got a concave up situation. Okay, so it's concave. Okay, so it's concave up, concave down, and then concave up again. Okay, let's take a look at our next example here. We've got this one good. Okay, perfect. Let's take a look at our next example here. All right, to sketch the graph. Okay, here's a different one we haven't seen. We might want to have Desmos handy so we can get an idea what this looks like by finding and analyzing the points of inflection. All right, so let's take a second and find the second derivative. We'll go to it and I'll be back in a minute. Okay, so I hope this is what you had for the first derivative and the second derivative. This is a relatively easy function to take the derivative and the second derivative of, so hopefully we're still at this situation. We've got some interesting thoughts here. Okay, I want to take a look at the results of the first and the second derivative and compare it to the function here. Now right off the bat we've got a bit of a problem here. It looks like the first derivative, evaluated at 0, okay, does not exist. Okay, so the slope of the tangent line at that original point in my function at x equals 0, I can't take. It doesn't exist. Okay, and what about, okay, or similarly, what about when, okay, I have, okay, the second derivative at 0. It's also a 0 in the denominator, also does not exist. Okay, but I do have, okay, a value when y is at, when x is at 0. So there does exist, okay, this point, the origin, on my original function, okay, but I don't have a slope of the tangent, okay, and I certainly don't have, okay, this inflection point or turning point. I can't take the value of it here. So what do we got? Well, we've seen that situation before, and like I said, I think at any time we want to maybe take a look at Desmos. So I have a point here, but I can't take the slope of the tangent, okay? Now, maybe we need to look at, okay, a couple other endpoints. Let's take a look at endpoints. Okay, and what happens when I have, okay, maybe the limit of my function. Okay. Okay, so that would be the limit of my function as x approaches negative infinity of x to the 1/3. Okay. Okay, so what happens there? well, if I've got a really large negative number and I take the third root of it, I'm going to have negative infinity. And the other endpoint is evaluating the third root of a really large positive number. And again, that would be infinity. So I have this situation, and I have that situation. Okay, now what's happening? Maybe take a look at the 0 here. What's happening around 0? And we can do that. Okay, we can do that by, checking, also limits here. So the limit as x approaches 0 from the, from the left side. Okay, what would that be? That would be very, very close to 0, but from below. And how about the limit as x approaches 0 from the right side of my function? And that would be over in this area here. And I think it would be approaching 0 from the right side. Okay. I know this. Okay, the slope doesn't exist. Maybe we've got the tangent line, and I think it's sort of looking like this. Now that's a pretty terrible sketch. I'm going to try this a little bit better. Okay, and I'm going to peek at Desmos and sort of see what happens here. Have I got any other situations I should take a look at? Okay, well maybe, maybe before I sketch this again, I've got my point. So I've got my point. Okay, and I've got, the slope of a tangent that doesn't exist. I've got that situation. Now, I should have, and I'm going to now, but I could have or should have taken a look at concavity, okay? Now, just because this, again, we've talked about this situation in here, clearly it looks like x equals 0 is some sort of important point on my function. So when my first derivative or my second derivative don't equal 0, almost like an asymptote in a sense, on the function it's a real value. But I think it's high time, and where I'm going with this, I think it's kind of high time that maybe I check this point, by way of sort of concavity here. Okay, and let's take a look at the second derivative of my function. Okay, so my second derivative of my function, and I'm going to use the function, negative 2 x to the 5 over 3, and I need a negative value in here. So if I have a negative 1, let's say, I'm going to have a negative over a, now if I put a negative, take the third root of a negative, it's still a negative, raise it to the 5th power, it's still a negative, multiply it by 9, it's still a negative. Okay, so I have, concave, a negative over a negative equals a positive, so I have a concave situation when x is less than 0. Similarly, if I use the point in the interval where x is greater than 0, let's say x equals 1, I'm going to have a negative, it's just negative 2, over top of a positive. And a negative divided by a positive is a negative, so I have concave down. And this really helps me understand what this function and graph looks like here, and that's certainly represented here with what I thought it was. Okay, so concave up, and concave down. Good. Well, does that help? And look, certainly. So we do have an inflection point, right? By its definition, we do have an inflection point. At x equals 0 is an inflection point. And it should be checked. If it's a point that does not exist, it still should be checked because an inflection point is like a turning point. And we see that there is a turn in this function at x equals 0, right? Okay, that might be it for the lesson, and it's certainly for some homework questions. And please make sure you continue with these homework questions and refer to the homework page within chapter 4 if you have any questions at all about particular homework questions.